Okay, I thought I'd look at getting started on exercise 410. In exercise 410, it mentions we have a arbitrarily defined random variable on AB. A is less than or equal to X is less than or equal to B. And, so here's A, here's B. Who knows what it does? Something on AB. And it says show that the mean is bounded also by AB. Okay, so what we want to show is that the mean of X is between A and B. So that's what you want to do there. And well, what do we know? Well, we know the mean of X is just E of X. And so we have an integral from, well, A to B, I guess. We could do minus infinity to infinity, but I think in this case it'd be better to do AB, X times f of X. And I think the thing to notice here is on this interval, the, let's see. Yeah, okay. I just was thinking about what if A is negative, but we're okay, or B is negative, but we're okay. So, what you know is that X here, the maximum it can be is B. So the maximum of X is equal to B, and the minimum of X is equal to A. And so if we bound this by separate integrals involving A and B on top and bottom, we should be able to get that answer. And then it says show that for part B that its variance is less than or equal to B minus A squared over 4. Well, again, I'd probably go with the fact that the variance is equal to our expected value of X squared minus m sub X squared. And so now it does get a little more complicated, I think, with this. And, that's where I think to start, I would assume, A and B are greater than 0. I'd start there just to see if that makes life a little easier. Because, again, we just have that integral from A to B of X squared, f of X dx minus mx squared. And so, it just seems if I start there with those both being greater than 0, then I know that B, of course, is greater than A, and I can have that the maximum here would be my B squared times that integral, but that's 1. And my minimum here would be the minus A squared. Okay, so there I've got, now that's not the same as the B minus A quantity squared. And So it may be that they're attacking this instead of using this calculation here, they may be using the centered moment of Ex minus m squared, like that. And because there we have that form there, yeah, actually I guess that is probably the way to go. So I think I would scratch this approach, and actually then I don't think you have to assume that, because so if we go with this integral from a to b of the x minus m squared f of x dx, then I can get that the x minus m squared, that is definitely less than or equal to b minus a squared. And again, they just want us to show the less than or equal to. So I've got the b minus a squared. Because x, I can make that as big as b, and m had to be between a and b. Okay, so and so I have the squared there. Good question as to where the 4 comes from. Because that's pretty obvious. But getting the 4 there, I don't know. I'm a little stumped on that. I may have to come back to this one. So I'm going to pause it for a minute. Okay. So the only way, what we need here is we want that thing to be less than this over 4. And I haven't really come up with a extremely quick way to do that. Mostly, what I see is looking at this sort of thing here, and saying, okay, well, what if you didn't use the mean there? And they say, well, let's define a function g of t equal the integral from a to b of x minus t squared f of x dx. And if you want to minimize that function in terms of t, then you need to take a derivative g prime of t, and so that's a to b of 2x minus 2t f of x dx, like that. And so what we see is that to make this 0, right, if we want this to be 0, we need t to equal x. Or in other words, what that means is we need this to be our minimum value is when t is the expected value of x, because x, it can't actually be x. X is changing, right? But if it's the expected value of x, then we can get that to be 0, because this other is just the expected value of x. So that's really what it comes down to, is that g of t is a minimum when t is the expected value of x. Well, so that means that if we take the expected value of our x minus m squared, that is going to be less than or equal to the expected value of x minus, and I think what we want here is a plus b over 2 squared, like that. Okay, so I'm going to pause for just a second while I make sure I've got this right. Okay, so I'm back and I'm wondering, you know, we had the interval b minus a squared over 4, or the inequality, and you know, what about this one? Could you say that you have something like that where m is the mean, and it, you know, it sort of seems reasonable, but it's not necessarily obvious. However, this one you can get without the derivative stuff if you start with, if we let a equal 0 and b equal 1, so we're on the interval 0, 1, then if you do your sigma squared, well, that's the expected value of x squared minus the expected value of x quantity squared. Okay, but what I know is that that would have to be less than or equal to the expected value of x squared is going to be less than the expected value of x. And so if we make this the expected value of x minus the expected value of x squared, like that, that's just our mean minus our mean squared, which is the mean times 1 minus the mean. Okay, and again, because we're between 0 and 1, I know that x squared is smaller than x. And so that's why I know e of x squared is smaller than e of x. The expected value of x squared versus the expected value of x. So that's how I got that. So I just got to use the fact that x squared is smaller than x on the interval 0, 1, and oops, I don't know where that came from. And so we get this, but you see this is saying this is the mean minus 0 times 1 minus the mean, or in other words, m minus a times b minus m. Okay, so that worked for 0, 1. Then what do you do after that? Well, if I let x be 0, 1, so x is on 0, 1, well, then if I let y equal b minus a times x plus a, then y is, is less than or equal to a less than or equal to b. And now, you know, I can use my variance stuff on here to say, okay, well, the sigma y squared, well, that's b minus a squared, and then times the variance of x. Okay, so we had that. But the variance of x, we know, is less than or equal to the mean of x. So let's see, b minus a squared. The mean of x times 1 minus the mean of x. Okay, because we established that up above. Okay, but we know that from this, the mean of y is equal to b minus a times the mean of x plus a. And so now solve for the mean of x. So, mean of x is equal to the mean of y minus a divided by b minus a. And so if I substitute that back into here, I end up with the inequality that I want because I've got my b minus a squared and then the mean of x, so I've got my minus a over b minus a. And of course, one of those is going to cancel. And then times 1 minus the mean of x, so that would be my minus a over b minus a. But when so I'm going to get rid of one of those. But when I get my common denominator, I get b minus my, so I get my minus a times b minus my. And then when I did this b minus a over b minus a to get the common denominators, I got rid of the other. And so there we go. So this is another inequality that's similar, but not quite the same. And so I just thought I'd add that to the end of that problem. That's I think a pretty rough problem because of that derivative. But this one at least you didn't have to, oops, did I go too far? No. I didn't have to enlist the derivative, but I did have to do some pretty fancy interval work here and some of our functions of random variables. So I kind of like it in that it's using the functions of random variables, but it wasn't the problem. So there we go.